And now we are going to play with magnets. By the end of this video, you should be able to explore the different properties of magnets with me, along with me. If you happen to have some magnets at home, go ahead and grab them and have some fun with me. Here is the timeline for today's lesson. It's basically an introduction to atoms. So first and foremost, what are magnets? What are magnets in general? And how do they work? What are their charges? We're going to play with these magnets and we're going to assemble them in different ways to try and formulate patterns and try and find things that make sense about the magnets. And then we're going to model atoms using the magnets and describing how these magnets are representing the different pieces of an atom. Magnets are some great fun. If you've never had the joy of playing with magnets, then let me demonstrate for you how magnets kind of work and how they can model an atom. What we see with magnets is that they have a force between them. Now, if you were going to play with these yourself, you'd be able to see that I am not forcing these two together. They are coming together of their own free will. There is a magnetic force attracting the two together. However, if I flip this over, suddenly the two do not want to come together. There's a force that is physically repelling the two, and it's very difficult to try and force them together. It's nearly impossible at this point. However, if I were to release this, it'll flip around and still attract to the other side. So we'll show that again. So here they are not wanting to be together, but if I release one, it flips and connects to the other side. Again, completely of its own free will. I didn't force the two together. That is how they came together. So with magnets, there are charges. On one side of a magnet, there is a positive charge, and on the other side of a magnet, there is a negative charge. So there are two different charges here that we're playing with. And just like in relationships, typically, as the adage goes, opposites attract. So if you have a positive side next to a negative side, those two want to come together. The positive and the negative want to be together. They're attracted to each other. Whereas if you have both of the positive sides or both of the negative sides facing each other, you can see that they don't want to be together very much. So let's go ahead and play around with these. Let's see what we can do with magnets. If we were to put some magnets here on the floor, we can see that some of them automatically flip and jump around to be attracted to each other. We can assume then that they are automatically forming according to their positive and negative sides, those opposites attracting to each other. So let's try this again. We put them out here like that, and for now let's just stick with 3. And we were going to try and put these together. Let's assume that we were trying to put all the same charge together here. And that would be pretty difficult, considering if they're all the same charge in the same area. Hold on one second. I will get my hand out of the way here in a second. Oops. This is harder than it looks, I promise you. They are tricky little devils. There we go. Okay. Alrighty. There, and they are all repelling right now. They do not want to be together. So if we're going to try and force them together in a small amount of space, and I let go, they're all going to move away from each other if you saw that. Of course, this one flipped in order to be together with opposites attract again. But in terms of wanting them to be together when they're all the same charge is very, very difficult. And they will repel. So what if we had something in between them? Like maybe some of these pom-poms, perhaps. Something in between them to stop them from wanting to repel from each other. So let's try and put the two sides together that want to repel. But let's put something in between them that might dampen that. Now, I can't grant you the feeling difference, but what I can tell you right now is that the force that this magnet is pulling on the other one, or repelling, is less now. Now that I have this little buffer, this little pom-pom, craft pom-pom between them, it is buffering that repulsion. Even more so if I stick another one in between them. Now the repulsion is even less between the two of them. It's not going to fly away nearly as violently as it did initially. I could keep going and keep putting more and more pom-poms as a buffer between these repelling charges. And soon enough, you're going to end up with magnets that don't mind being around each other, even though their charges are the same. So if we were to do that, all down here, let's put a whole bunch of these around, then suddenly we can have a system where all the magnets are pretty comfortable being near each other, or at least they're tolerating each other for now. Now, if we took other magnets, let's say we took 3 other magnets, and we put them around the outside, what we can see is that at a certain distance, if we keep inching this one closer and closer, at some point there's an attraction between the two. That would imply that these two magnets are attracting due to opposite charges. So one would be positive and one would be negative. In an atom, we have a nucleus, something in the center that is all positive charge. These red pom-poms are representing neutrons. Neutrons are something that don't have a charge. Notice that if I try and take 2 pom-poms and stick them together, it's not like they're going to stay stuck like the magnets did. Contrary-wise, 2 magnets stick together on their own accord. 2 pom-poms, not so much. They have a neutral charge. These pom-poms are therefore neutrons. Both the protons and the neutrons are in the center of the atom. They're in the nucleus of the atom. And it's necessary so that these protons don't repel away from each other. These magnets on the outside represent electrons. Electrons are negatively charged, and they're much, much smaller. So the model is not quite accurate. These would be hardly even visible in comparison to a proton in the nucleus. However, they are going to be on the outside, circling around this nucleus in 3D space. So they could be up here, they could be below it, they could be all around. And there's no way of knowing exactly where one of these electrons are going to be. They're just kind of buzzing around, and they have a density around the atom, so a probability of finding one somewhere or another. These electrons, since they are negatively charged, are attracted to the protons in the center, in the nucleus. And because of that, they tend to stick around the nucleus. There's a higher electron density around the nucleus, where there's a stronger force, a stronger pull, than the electrons that would be farther away. Notice that as we did before, as we inched closer, they literally came together on their own accord. But the magnet out here is not pulling the magnet from over here. The force is less with a greater distance away from the nucleus. So what we've modeled here then is a lithium atom. Lithium has 3 protons and 3 electrons. This would be representative of the positive and neutral charge in the middle of a lithium atom, and the negative electron charge buzzing around the nucleus of a lithium atom. That's all I got for you on this one. Please show a duck some love and subscribe to my channel. Thanks!